we consider hydrogen molecule. The hydrogen molecule, there are two electrons that form a covalent bond between the two hydrogen atoms. Now, if you look at a rough description of a really simplistic overview of this structure, then the electron cloud, the molecular orbital as it is called, if we look at the bonding molecular orbital, then there are two electrons in this orbital. Now, it's impossible to identify the individual identity of the two electrons. It's impossible to say that one of the electrons belongs to one atom and the other electron belongs to another atom. For all purposes, these two electrons are really indistinguishable because they share the same wave function. So identical particles which are indistinguishable particles means they must be identical particles. You can distinguish between an electron and a proton because they are non-identical particles. But when we say that indistinguishable particles, then these particles, it's implicit in indistinguishability that these are identical particles. So two electrons can be indistinguishable, two protons can be indistinguishable. So quantum mechanics has a special formalism of dealing with these indistinguishable particles. For example, if you have a metal in which there is a sea of electrons, the free electrons, it's not possible to talk about the individual identity of electrons. All the electrons are totally indistinguishable, they are just the same. So how do we deal with indistinguishable particles in this context? First of all, let's consider two particles. Each one of these particles is in a particular state, say A. The second particle is in a state B. Okay? So we write a tensor product A cross B, which can also be written as A comma B or A, then A, then B. Right? So these are different notations. Now let's suppose that the question that we would like to pose is, what states are possible for this bipartite system when the particles are indistinguishable? Can we have states of this kind? Get A, get B, where A is equal to B or A is not equal to B. Can we have two particles in the same state, in the same quantum state? Can we or can we not, for example? If we have two particles in different states, which means A is not the same as equal to B, then is such a direct product allowed quantum mechanically? So these are deep connotations in this concept, and as we go through today's lecture, we learn these connotations. Now suppose I define an operator called the exchange operator or the parity operator. What the exchange operator does is, let me define it as, denoted as P1, 2. If I have the state get A cross B, then implicit in this ordering is that this state belongs to the first particle and this state belongs to the second particle. Okay. So I can draw these subscripts and the ordering will tell me which particle is which. So if I apply this exchange operator onto this state, it will simply swap the labels. For example, particle number 1 would then be in state A and particle number 2 would be in state particle number 1 would be in state B and particle number 2 would be in state 1. We'll just exchanging the labels. So the effect of this operation is simply B crossed with A. Okay. So if I take two particles, if I would like to represent this graphically, and if these particles are spin half particles, and if I'm only interested in the spin half degree of freedom, if this is say ms plus half, this is ms minus half. This particle is at some location R1, position vector R1. This particle is at some position vector R2. Okay. So now I have two degrees of freedom, a spatial degree of freedom and a spin degree of freedom. So the state of this bipartite system is really for the first part. This I'm labeling this particle as 1 and I'm labeling this particle as 2. Okay. So the state of this system before the exchange operation is, say, R1, which denotes the position, comma 1/2, which denotes the value of ms. This is the first particle, right? Crossed with R2, comma -1. Okay. This is the state of the bipartite system. Now I apply the exchange operation onto this. What this does is that it simply relabels this as particle 2 and puts the label 1 here. Okay. So this becomes particle number 2, this becomes particle number 1. And all the attributes of the particles are also exchanged, which means that after the exchange operation, state would become, the particle 1 is in the state R2, comma, -1/2, tensor with. Now this has become the first particle. Okay, and the second particle takes up the attributes R1, comma, +1/2. So the labels have been exchanged. So this is the effect of the parity operation. Now this parity operator has certain properties, certain important properties. If I have a quantum state of psi, a multipartite state of psi, if I exchange any two particles in that multiparticle state, 1 and 2, then my output should just be psi, the original state, with some phase factor, delta. Why is that? The reason is that the physics should not change if I interchange the labels. Okay. So if I have some desired final state, psi f, and I would like to find the probability of projecting the initial state on psi f, then this probability in model squared, which is this model squared, should not depend upon whether I use psi or its exchanged version. Okay, so if I'm just changing the labels, the probability that I project onto the same state should not change. Probability should be independent of the swapping process. So according to this description, this should be equal to psi f. And this is only possible when this is just a global phase factor, when there is just a global phase factor for this psi. You can prove this on your own, it's just a 1 minute. Now this also means, we also know that if we apply the projection of this exchange operator twice, we should recover the original state. Okay, now this should be psi. What this means that this EI psi can only be +1 or -1. Because then EI2 delta must be equal to 2 pi. Or 0. Delta must be 0, which means this should be 1. Okay, or 2 delta is 2 pi, between delta must be pi, which means that this must be -1. So if I have the exchange operator acting on a state, okay, then there are only two possible values for EI delta, plus psi and minus psi. Alright. Which means that every multiparticle state is, now this is independent of what state we choose. So every multiparticle state is an eigenstate of the exchange operator with eigenvalues +1 or -1. Now nature has some role to play here as well. Nature it classifies the particles into two categories depending upon whether this sign is positive or this sign is negative. For positive sign particles, this means the particles are called bosons, and negative sign particles are called fermions. So for bosons, if you exchange any two particles in a system of bosons, the new quantum state after the change process is totally identical to the initial state with no phase factor. And if you have a set of fermions and you exchange the identity of two fermions, for example, you swap the attributes of two electrons, then the new wave function that is formed is negative of the original. Okay, it picks up a global phase factor of pi. Okay, and the particles are classified into these two groups, bosons and fermions. Now, for example, let's consider this two particle state AA. This is symmetric under exchange. So if you swap the attributes of the two particles, you will get the original state. Okay. A, B is also symmetric under exchange. Okay, so I am trying to define what is meant by symmetric and antisymmetric. However, what about this A, B? If I have this two particle state, is this symmetric or antisymmetric? If I apply the exchange operation on this, I get B, A. Is this related to A, B in some sense? No, it's not. So it's neither symmetric nor antisymmetric. Okay? So the exchange operator only has as its eigenstate symmetric or antisymmetric states. This will be an eigenstate of the exchange operator. This will be an eigenstate of the exchange operator. However, A, B will not be an eigenstate of the exchange operator. Okay, so minus A. There's no such thing as minus A.
So what would be the antisymmetric state?
Of what?
Of A.
No.
Antisymmetric eigenstate.
Let's find those out. So we're talking about two-dimensional Hilbert spaces, right? And two particles which are each one of them is two-dimensional. So we're talking about a bipartite system. And the basis states these are the basis states of each Hilbert space, right? And these are mutually orthogonal, let's consider that. So if you look at the exchange operator, what are the eigenstates of the exchange operator? Okay, of course one of them is, right, this is one eigenstate with eigenvalue plus 1, correct? Another eigenstate is B, eigenvalue plus 1. Both of them are symmetric under exchange. However, what about A, B and B, A? So since it's a four-dimensional operator, it must have four basis states. So these are two of them. So if you would like to find the eigenstates and eigenvalues of P1, 2, you would like to write this in matrix form. So this is clear. So this is 1 here, there's a block here and 0, 0 everywhere. Okay, and the ordering that I'm using is A, B, B, A, B, right? So I'm writing the exchange operator in matrix form, representing it in the basis that I've chosen, in the direct product basis, in the uncoupled basis, in other words. So we've learned that the uncoupled and the coupled basis stand on equal footing and one can interconvert using a Clebsch-Gordan coefficients. Okay, it does not matter which basis you choose, but as far as the parity exchange operator is concerned, there is a preferred basis. Let's see what that is. So if I use this ordering, which means the columns are also ordered likewise, then this is the form that I have. Now this block here is, since A comma B and B comma A are not eigenstates of exchange operator. Right? Therefore, I can write this operator separately. This is, I write this block separately. I have A comma B, P12, A comma B, A comma B, P12, B comma A, B comma A, P12, A comma B, B comma A, P12, B A, right? So this is this block that I've written here. Now this element is 0, of course it's 0, because if I swap A and B I get B A, and B is orthogonal with A comma B. So this is 0, this is 1, and this is 1. So this is just a sigma x operator. So what are the eigenstates then? The eigenstate would simply be superpositions of A comma B and B comma A. So the two eigenstates, these are two eigenstates, the other two eigenstates are 1 over under root 2 A comma B plus B comma A. This is one eigenstate, and the fourth eigenstate is 1 over half A comma B minus B comma A. And these are just the coupled basis states. So for the exchange operator, the four basis states are the coupled and the uncoupled basis states. These are the four eigenstates. These three eigenstates, 1, 2, 3, they have eigenvalue 1 and this is eigenvalue minus 1. So these three states, which are really also a form of the triplet states, these are eigenstates of the exchange operator and have even parity, which means that they are symmetric under exchange, whereas this state is anti-symmetric under exchange. You apply, for example, you take this state, okay, 1 over under root 2 A comma B minus B comma A. You apply the exchange operator here, 1 over under root 2, A comma B becomes B comma A, this becomes A comma B. This is simply negative of the original A comma B minus B comma A. Okay? So this state is anti-symmetric under exchange, whereas all the other three states, the ones that I've written over here, these are symmetric under exchange. Okay? Now all quantum states must be symmetric or anti-symmetric under exchange because of this physical causality principle that I've written over there. They must have eigenvalue plus 1 or minus 1. Okay, so if you have two indistinguishable particles, they can exist in this state A comma A because this is symmetric under exchange. They can exist in B comma B, but they cannot exist as A comma B because this is neither symmetric nor anti-symmetric under exchange. So when we have identical particles which are also indistinguishable, for example, two electrons, one electron is in my pocket, one electron is in Saad's pocket. These are not indistinguishable particles because they belong to different Hilbert spaces, they belong to different possessors. Okay? So our Hilbert spaces don't overlap, which means that our wave functions don't overlap. So these are distinguishable particles. My electron is tagged with Sabi, his electron is tagged with Saad. However, if you have two electrons that, for example, form a bond which share a wave function, which have the same wave function, then these become indistinguishable particles. Or you have a Bose-Einstein condensation, which all the bosons are indistinguishable, or you have superconductivity, which all the Cooper pairs are, which are bosons, they are indistinguishable. Then for such indistinguishable particles, you cannot have states, arbitrary states. For example, you cannot have this state, A comma B, because it's neither symmetric nor anti-symmetric under exchange. So two indistinguishable particles must be in either of these four states. Okay? And this is also called, this postulate that two indistinguishable particles must be symmetric or antisymmetric under exchange. This is also called the symmetrization postulate of quantum mechanics. Also called the Pauli principle. And don't confuse this with the Pauli exchange principle. The Pauli exchange principle or Pauli exclusion principle is a special version of the Pauli symmetrization postulate. Okay? It's a stronger version. Okay, it's a special case. For example, if you have two photons, let me give you an example. If you have two photons, and we look at the polarization degrees of freedom and the linear momentum degrees of freedom. Photons have linear momentum, which is a k vector. Suppose I have two photons. Plus q. Suppose I just consider the linear momentum of two photons. One is p, the other is q, and p and q are mutually orthogonal. Okay, these are just labels for the linear momentum. Now photons are bosons. They have spin 1. Okay. Now the quantum state of such a boson, of such particles must be symmetric under exchange. Now is this a symmetric state? Yes, it's a symmetric state. If I also consider, however, I also need to consider the polarization state of the photon. Because I have to swap all the attributes of the particle. The particle will have linear momentum, it will have polarization. Okay. So if I write this state, 1 over under 2, if I write the same state and conjoin it with the polarization state, suppose I have 1 over under 2, left polarization, right polarization, minus right circular polarization, left circular polarization. Now just looking at this, is this symmetric or anti-symmetric exchange? Anti-symmetric. So an anti-symmetric is being multiplied off with a symmetric to give an anti-symmetric. So the entire state is anti-symmetric under exchange, which is not allowed for a boson. So this will be a non-allowed state for two photons. However, if you put a plus sign here, then this will be symmetric under exchange. Okay, an interesting example is provided by para-hydrogen, which is a spin isomer of hydrogen, but maybe I'll ask that in an exam. Okay, so look up para-hydrogen, a spin isomer of hydrogen. So you swap any two attributes of the complete attributes of any two particles. It should either be symmetric or anti-symmetric under exchange. So nature does this classification for us. It classifies all particles into boson and fermions. One of them is symmetric, other is anti-symmetric under exchange. You don't have to worry about it. So bosons generally are particles with spins. They are particles with spin 0, 1, 2, 3. Integer spins. Okay. And fermions are particles with half and their integral multiples 3 by 2, 5 by 2, and so on, right? These are fermions and these are bosons. Let's look at an example. Identical, indistinguishable particles in one dimension. Now suppose we have an infinite well, right, and two electrons are inside this infinite well, and it's impossible to distinguish between those two electrons, right? You have two electrons, they share the same space, they are in the same Hilbert space. It's impossible to talk about, you look at, it's not possible to look at one electron and track it, okay, because of quantum mechanical principles, okay? So these two electrons are totally indistinguishable. Now what we have is two electrons in an infinite well. We know that for a single particle, the wave function is, if L is the length of the well, sine n by x over L, right? And energy is n square pi square h bar square over 1n square. Okay, so n is the principal quantum number. Now we have two particles and they are indistinguishable, identical particles. Let's suppose number one that the particles are distinguishable. For example, we have an electron and a proton inside this well. Okay, distinguishable particles. Okay, let's look at distinguishable particles first. So the ground state of such a system will simply be psi. Now for the ground state is when n equals 1 for a single particle state. So the ground state for two distinguishable particles will be psi x, let's call it g for the ground state. Okay. So now we have two variables, x1 and x2, identifying the two particles. So this will be equal to, for the first particle, and these particles are non-interactive, we don't interact with one another. So 2 comma 2 over L sine of, for the first particle n is 1 pi x1 over L. For the second particle it's sine of pi x2 over L. So this is the ground state for these distinguishable particles, and the total energy E in the ground state is n1 is n1 for second particle. This is just going to be equal to pi square h bar square 2nl square. N is 1 for each particle. Okay? So for two particles it's going to be 2. 1 plus 1 is 2. Suppose both of them are electrons but somehow they are distinguishable. For example, protons, okay? These are distinguishable electrons. It's a hypothetical scenario. Now, this is just the direct product of two single particle wave functions, right? Right? Just the direct product of two single particle wave functions, isn't it? Remember, here I am taking the liberty of writing a cross product between wave functions. Okay? Generally, I have been writing cross products or vector direct products between gets, but this also makes full sense. I'm just showing that the wave functions are factorizable. You take the total Hamiltonian. The total Hamiltonian for this system will be just P1 square over 2n for the first particle and P2 square over 2n for the second particle for x inside the well, right? And there is no interaction term. So what you could do is you could find the eigenstates of this Hamiltonian, the eigenstates of this Hamiltonian, the eigenstates of this Hamiltonian and this Hamiltonian are simply the single particle wave function, and then you take the direct product of the wave functions. So it's factorizable, everything is factorizable here. If you would like to find out the first excited state, psi e, this means that psi e x1, x2, this state will be doubly degenerate, because you could either have psi 1 to x1 comma x2, that is first particle is n is equal to 1, second is n equals to, or you could also have psi 2 1, right? So we get a doubly degenerate state. Okay? Let me write one of these states. One of these states is 2 over under root L sine of pi x1 over L, 2 over L under root sine of 2 pi x 2 over L. Okay. And the other degenerate state, we have a 2 here and a 1 here. Okay, so this is what we normally do, what we've been looking at so far in quantum mechanics. Okay, this is a doubly degenerate state, excited state, and the energy E12 will be equal to E21. And if I call this alpha, some alpha, the energy will be equal to, what will the energy be equal to? 5 times 1 plus 4. move on to indistinguishable particles. Homework दे दिए आपने? जी? अच्छा, indistinguishable particles. Now there are two kinds of indistinguishable.
स्टेट अगर यहाँ पे 2 आ जाए यहाँ पे 1 आ जाए तो इस केस में x1 इक्वल टू x2 होना चाहिए मतलब उसके
The x1 is just identifying the label of the first particle, x2 is the position of the second particle. तीसरा में जहाँ position vectors लिखे थे ना r1 और r2. अच्छा, let's look at indistinguishable particles. There are two kinds of indistinguishable. Let's look at bosons first. Which is symmetric under exchange. You cannot talk about the position of the particles away from functions. Talk about expected value. So if you want to find expected value of the particle, you would, of the first particle, you would find this of x1. If you want to find expected particle of position of second particle, you find this. Okay? And if you would like to find out the distance between these particles, you find x1 comma x2. Say the distance away, right? Now if bosons, let's look at the ground state for these bosons. Psi g, x1, x2, bosons. Now since these are bosons, the wave function, any wave function, ground or excited, must be symmetric under exchange. Okay? So we know the ground state wave function 2 over L sine n pi x over L. So the ground state will simply be equal to 2 over L sine of pi x1 over L 2 over L sine of pi x2 over L. Right? So this is the ground state. It's symmetric under exchange. It's just like writing A cross to A. Okay? And the energy of this ground state is going to be equal to 2L. Okay, both of these particles, they are labeled by the position labels x1 and x2, but you write a wave function that is symmetric under exchange. Okay. Now if you would like to write the first excited state for these bosons. First excited state can also be symmetric or it has to be symmetric. Okay. Now comes the difference. If you look at this state, the first excited state, if you look at this state, this is neither symmetric nor anti-symmetric under exchange. Because this is sine pi x1 over L, this is sine 2 pi x over L. Right? So this is like A tends to B. However, you can have states of this kind for distinguishable particles. Correct? Therefore, if you would like to have a state that is symmetric under exchange, the only possibility of having such a state is to produce a state of this kind. And this state is non-committal. Non-committal in the sense that it does not tell you. For example, looking at this state, you can't tell whether the first particle is in state cat A or cat B. Because you can't distinguish between the two particles. You can't tell which particle is in which state. So this is non-committal. This state is non-committal in the sense that it cannot specify whether particle A possesses this set of attributes and particle B possesses the orthogonal set of attributes. Particle A possesses both attributes and particle B possesses so it's non-committal. Okay, non-committal means you don't commit what attributes does particle A possess and what attributes does particle B possess. It's non-committal in that sense, and it's symmetric under exchange. So the only possibility of writing the first excited state for the boson is 1 over under root 2 over L. So I'm just multiplying on this 2 over L. Sine of pi x1 over L sine of 2 pi x1 over L plus sine of 2 pi x1 over L sine of pi x2 over L. So this is the first excited state. And it's an eigenstate of the parity operator, of the exchange operator, with eigenvalue plus 1. Symmetric under exchange, so that it has to be true for bosons. Okay?
So when we said psi1 2 and psi2 1, did it mean the same thing? And
ये दोनों नहीं, इसमें first part ये distinguishable है. First particle is in state 1, is in n1, second is in n2. This first particle is in n equals 2, second is in n2. So these are different states, different eigenstates, but with the same eigenvalue. Okay, so this is the first excited state for two distinguishable bosons in the infinite well. Its energy is again 5 electron. How will you find this energy? You can just have the Hamiltonian acting on this state, right? Psi E. The eigenvalues will be E, right? And this will just be the eigenstate. Okay. Other thing is that is this a degenerate state? No, it's not a D. So degeneracy, it's non-degenerate state. In other words, degeneracy has been lifted by symmetrization. Okay, so this is a non-degenerate state. You cannot find any other state which has the same eigenvalue. Okay. Now let's look at fermions. Like 2 electrons in an infinite well. This could be 2 photons in an infinite well. So the fermions, all states of the fermions must be antisymmetric in an exchange. So neither of these states is allowed. So the fermionic ground state has to be of this form. In other words, you cannot have 2 fermions in the state ket A cross to ket A or ket B cross to ket B. It's impossible to have 2 fermions in this state, which means that 2 fermions cannot have the same quantum state. This is called the Pauli exclusion principle. Okay? 2 fermions cannot have the same quantum state. Okay? Just by definition, because they have to be antisymmetric under exchange. So if they have the same quantum state, they will be symmetric under exchange. That's not allowed for fermions. So this is called the Pauli exclusion principle. So the ground state for 2 fermions x1, 2 has to be equal to 1 over 2 L sine of pi x1 over L sine of 2 pi x2 over L minus sine of 2 pi x1 over L sine of pi x2 over L. You cannot have pi x1 over L, pi x2 over L, because then the two formulas will be in the same state, will be in the same quantum state. Remember, x1 and x2, these are just the position coordinates of each of these particles, and they will help in tracking down the expectation values. Okay, these labels, this is x1 and x2, both of these are coordinates in the same space, in the same Euclidean space in which the infinite well exists. So if I write sine pi x1 over L into sine pi x2 over L, this means that two electrons are in the same quantum state, but that's not allowed. So if you have a 1 here, n equals 1 here, you must have n equals 2 here. And then we must form the antisymmetric superposition to form the ground state. So the ground, this is the ground state, and its energy, you can find out this energy. The ground state energy is going to be 5 alpha. Now how will you do that? You will just take this Hamiltonian operator, H, okay, this is P square over 2m, P1 square plus P2 square over 2m, right? But what are these P's? 1 over 2m minus H bar square partial x1 square plus partial x2 square, right? So you take this Hamiltonian operator, act it on this ground state. Now becomes the role of x1 and x2 becomes clear. When you are differentiating with respect to x1, this will be treated as a constant. x2 will be treated as a constant. And when you are differentiating with respect to x2, x1 will be treated as a constant. So this is the role of, this is the only role of x1 and x2. But remember, they share the same physical space, both of these electrons. Now if you have this operator act on this state, this is an eigenstate because it's a ground state. It is an eigenstate of this. However, the eigenvalues will be equal to 5 times alpha, which will be the energy of this state. एक मिनट देता हूँ मैं आपको इसको आगे चलेंगे, हम एक exchange forces की बात। Now you will have a recitation this afternoon which will discuss the helium atom as an example of the symmetrization postulate. However, in these last 15 or 20 minutes, I'm just going to talk about exchange forces, and I'm putting these forces in inverted commas because this symmetrization postulate leads to apparent forces between particles. Okay, so this is a very exciting concept. Now suppose we have two distinguishable particles. One of them is in the state A, the other is in B. Okay. So if I write the wave function for these particles, I could write psi A x1, where x1 is the position of the first particle, A is the label for the quantum state, and psi B x2. Okay, so this is a ground state for two distinguishable particles. For two indistinguishable bosons, the ground state is going to be 1 over under 2 psi A x1 psi B x2 and the symmetric superposition psi B x1 psi A x2. And for fermions, it's going to be 1 over under root 2 psi A x1 psi B x2 minus psi B x1 psi A x2. Now what I am interested in is calculating for each of these cases the expectation value of the square of the distance between these two particles. Okay. How far are these particles? So this I know x1 is, I know that this is going to be x1 squared plus x2 squared minus 2x1 x2. So this is simply going to be x1 squared plus x2 squared minus 2 times x1 x2. So for each of these cases I have to calculate the expectation value of x1 squared, x2 squared and x1 x2. Okay, so let's work out the case for distinguishable particles. Let's work out this deviation for distinguishable particles. So, which means I would like to first calculate x1 squared. Now, x1 squared's expectation value is going to be equal to x1 squared. Okay, we take the wave function and its complex conjugate psi A star x1 psi B star x2 psi A x1 psi B x2, right? Okay. Now my variables of integration are both x1 and x2. So I have dx1 dx2. Okay. So I have integration of two kinds of variables, x1 and x2. ये मल्टी पार्टिकल्स की पहले जब हम एक्सपेक्टेशन वैल्यू निकाल रहे हैं, ठीक है? So now if psi ax1 is normalized psi bx, all the psi ax and psi b, both of these are normalized states. Okay, so if I look at this term and I look at this term and I integrate with respect to x2, nothing else has x2, it will just give me 1. Okay, so I'm left with x1 squared psi a and psi a, right? So I'm just left with the expectation value of x1 squared, right? But this particle is in state A, cat A, right? So this answer is just going to be the expectation value of, which is just the expectation value of x when a single particle is in the state A. So this integral that I have written on the top really becomes x1 squared psi a x1 psi a x1 dx1 over x1 x2 psi b star x2 psi b x2 dx2. ठीक है? I've separated out the x1 and the x2. This is 1 because the state B is normalized over all of space. Correct? And this is 1. Now what is this? This is simply x1 squared psi a x1 modulo squared dx1. So this x1 is immaterial. x1 is just a label for the position of the first particle. It's just a coordinate, it's a running variable. So this is just the expectation value of x squared. Given that the particle is in the single particle, this is a single particle waveform expectation value. Given that this particle is in the quantum state A, this expectation value will be different from the expectation value when the particle is in state B. Okay? So I've calculated x1 squares expectation value. Likewise, this expectation value will be x squares expectation value when the state is B. Because the second particle is in the state B. So this is calculated, I have to calculate the expectation value of x1 product with x2. You can go calculate it. x1 product with x2 is equal to x1 psi A star x1 psi A x1 b x1. This is x1 x2 psi b star x2 psi b x2 bx2, right? This is simply x expectation of A, x expectation of B. So for distinguishable particles, the square of the deviation between these particles is given by x squared when the state is A plus x squared when the state is B minus 2 times x expectation value of position in the state A, expectation value of position in state B. So what we've done is that we've reduced these expectation values to the expectation values of single particle states for distinguishable particles. Okay, so this is the case for distinguishable particles. Now let's look at indistinguishable bosons first. Bosons, distinguishable boson in the ground state. First of all, I would like to find x1 squared. So x1 squared is simply going to be equal. Now, the state is over there. Okay. So x1 squared, the complex conjugate of the state over there. So I put a 1 over under root 2 into 1 over under root 2 half psi A x1 complex conjugate psi B x2 complex conjugate plus psi B x1 complex conjugate psi A x2 complex conjugate, and all of this is being multiplied by psi A x1 psi B x2 plus psi B x1 psi A x2. Okay, B x1 B x2. So this is an integral. Okay, I have to calculate this and compute it. Okay, no fears. Now I will get, when this is multiplied multiplied by this, I get psi A x1 modulus squared, psi B x2 modulus squared. When this is multiplied by this, I get psi B x1 modulus squared, psi A x2 modulus squared. Now when this is multiplied by this, I get psi A star x1, psi B x1, psi B star x2, psi A x2. When this is multiplied by this, I get psi B star x1, psi A x1, psi A star x2, psi B x2, B x1, B x2. Now, if I look at this first term, now this first term, this 1/2 remains where it is. This is just x squared. Okay. This is just x squared in the state B. Now let's look at these terms. A and B are orthogonal states, remember this. Now, if A and B are orthogonal states, now, right. What will be this term equal to? This term multiplied by x1 square integral. What will it be equal to? 0. Because of this fact. dx2 psi b star x2 psi a x2 is 0. Because A and B are orthogonal states. Orthogonality. So this is 0, this will be 0. Correct? When two states are orthogonal, this is satisfied. This is what is meant by orthogonality. If I have two states A, B, what does their orthogonality mean? Their orthogonality means if I write B, Q, if it's a one-dimensional A, X, X, B, right? Now this is the wave function. This is simply dx, the wave function in the state A, complex conjugate. This is the wave function in the state B. If these are orthogonal, this must be 0. So this term for bosons equals this. This is symmetric under A and B, so this must also equal x 2 squared. Alright. Now I have to find out x1, x2, the expectation value of x1 and x2. How do we get this? This? In first term. Now this first term simply x1 square psi a x1 modulus square dx1 multiplied by psi b x1 modulus square dx2, right? Now this first term is equal to this. Now this equals 1 because the wave function is normalized. So I'm left with this. This is just the expectation value of x squared when the particle is in the quantum state A. Okay. Now I have to calculate x1, x2's expectation value. But this expectation value will simply be, I'll just put in x1, x2 here. Instead of x1 square, I just put in x1, x2 here. So there will be x1, x2 here, x1, x2 here, right? Instead of x1 square, there will be x1, x2. Okay. Now if I calculate the integral, instead of x1 square as x1, x2, so I have expectation value of x1 in the state A, which is xa, multiplied by the expectation value in the state B. ठीक है ना? इसी तरह this will be expectation value of A multiplied with expectation value of B because I have x1, x2 here. So we get 2 times this. Alright? However, now these terms, the third and the fourth terms will not be 0. Because, and remember I also have a factor of half here, so I put a half here. It is half. Now I will have plus 1/2 x1 psi A star x1 psi B x1 multiplied by x2 psi B star x2 psi A x2, okay, plus the fourth term. Plus, now this fourth term is just a complex conjugate of this term. Right? Plus, I just said complex conjugate. So my expectation value of x1, x2 is just this plus this. And dx1 here, dx2 here, right? Now I define this integral. This is an integral which involves states A and B. Give this integral a special, give this expectation value a special symbol. I call it x AB. Okay. I call this integral x AB. It has joint effect of both the states A and B. Alright. Now what is this state? This is x. This is x AB complex conjugate. हाँ बोलो. मैंने इस इंटेग्रल को जो एक्सचेंज इंटेग्रल कहलाएगा, इसको x की एक्सपेक्टेशन वैल्यू है ना, and I am labeling it as x expectation value AB. Okay, this is a label for this. Now notice that this is simply x BA. If I use this definition, this is x BA.
So वहाँ पे the evaluated similar integral to be 0.
नहीं, similar integral 0 इसलिए था क्योंकि यहाँ पे x1 square था सिर्फ. x1 x1 स्क्वायर था, यहाँ पे कोई x2 की टर्म नहीं थी, तो जो x2 की टर्म्स थी उनके बगैर जब इसको इंटीग्रेट कर देंगे with respect to x2 you get 0. Now you have x1 into x2, so you this is x1 here and x2 here. Okay. Now notice that this term is xab. Okay, I call it xab. This term is xba. Okay. Right. Since these particles are indistinguishable, so this term must be the complex conjugate of this term. If I take the complex conjugate of these values, I get xb star and I get xa. So this term is just a complex conjugate of this. Correct? So this term in itself is simply xab modulus squared. But then I have its complex conjugate as well. So I will repeat the same procedure for the complex conjugate term. I will get the same term and then put a 2 sign of 2 here. Hence, the x1, x2 expectation value is simply going to be equal to xa, xb, xb plus x ab modulus square, where x ab is defined as x psi a star x psi b x dx. Okay, so this is x1 x2. The total deviation x1 minus x2 modulus squared expectation value is therefore given by half of this plus half of this is 2 times this plus this x squared a plus x squared in the state b minus 2 times is 2xa xb minus 2 times xab modulus square. So this is for indistinguishable bosons. For distinguishable systems we had x squared a plus x squared b minus 2 times this. Okay. So this is for bosons. This is for distinguishable particles. And if I repeat the same calculation for fermions, I will get x squared a plus x squared b minus 2xa xb plus 2xab.
ये 2 कैंसिल नहीं हो गया हाफ
Sorry?
के से 2 कैंसिल नहीं हो जाएगा हाफ के से
स्क्वायर वाला
Sorry.
So
This is for fermions.
x से x b को भी
Extremely important result. What this result is telling us is that bosons and fermions differ from distinguishable particles in their average distances, in the square of their average distance. We're taking the scale because average distance will be positive or negative. Squared just gets rid of this sign ambiguity. Okay? So this is the average distance between average deviation squared between distinguishable particles. For bosons, this is always a positive term, right? So minus a positive term is always smaller. So bosons tend to cling together. Fermions, on the other hand, tend to go further apart because of this positive term. There is a positive sign. So this means that this symmetrization imposes a kind of force on the particles. Bosons tend to cling together and fermions tend to go away. Okay, and the difference lies in this exchange integral. So this is called the exchange integral. This exchange integral, in fact, is an important integral. It describes lots of processes. It describes all of magnetism. So if you were to take a course of condensed matter physics and if you were to study magnetism in detail, this is the starting point. Because it's the exchange interaction that makes objects ferromagnetic, anti-ferromagnetic or ferrimagnetic. Alright? So one last example, just 2 minutes. If you have 2 electrons, for example, there are 2 protons and 2 belonging to 2 hydrogen atoms and they would like to form a bond. Now electrons would tend, so if I were just to draw a rough picture of an electron cloud, the electrons tend to space themselves further apart. Okay, and bosons tend to cling. So if I have 2 protons, 2 electrons would tend to be further apart. Okay, so the cloud would go here for the electron and the cloud would go here for the electron. So if I look at the force that acts on the proton, the force that acts on the proton due to this electron is in this direction, right? And the force that acts on the proton due to the electron is in this direction. So no bonding should be possible. Okay, so the 2 hydrogen atoms cannot form a covalent bond to produce the hydrogen molecule. But you know that the hydrogen molecule is energetically favorable as compared to separate hydrogen atoms. So why isn't the bond formed?
So hydrogen atom itself is a boson?
नहीं,
half ऐड हो गए प्रोटॉन और इलेक्ट्रॉन का
नहीं,
सर
हाइड्रोजन एटम बोसॉन क्या है? आफ्टर कि बॉन्ड क्यों नहीं बनता? ये फर्मियंस हैं, ये सेपरेट आउट होने की कोशिश कर रहे हैं, बॉन्ड क्यों नहीं बनता? इस रूप से नहीं बनता, फर्मियंस तो दूर दूर जाने की कोशिश कर रहे हैं। उसकी वजह से स्पिन वेव फंक्शन आएगा, शाबाश। We have to take into account the spins of the electrons as well. The total wave function for the electrons. The total wave function of the electrons, right? 2 electrons has a spatial part and has a spin degree of freedom. Okay? And the total wave function has to be antisymmetric in exchange. Now, if we have these exchange forces, the fermions tend to be apart, right? So the ground state wave function is what we wrote over there. So if we have a spatial part, right, psi R1, R2, okay, this is being multiplied by spin part for the two, a spin wave function for the 2 electrons. Okay. Now, if these electrons are fermions, then they cannot have the same wave. They cannot have the same wave function, right? I mean, they cannot have the same quantum state. So their spin states must be in the singlet state. If these 2 electrons if these 2 electrons form a bond, then you should have a situation like this. These are the protons, and the electrons cloud should be overlapping like this. Okay, so that a bond is formed. This is called a sigma bond. So this molecular orbital is formed, which lowers the energy so that the 2 electrons are in the nuclei, so that the forces that are acting on the nuclei are on this direction, so that a bond can be formed. So these electrons must be in the linear in the overlap region between the 2 protons. Their atomic orbitals must combine in this way, right? This means that the wave function of the electron cannot be of the two electrons cannot be in the fermionic state that is written over there. If a bond is to be formed, the wave function of the two electrons has to be of this kind. Psi 1 over under root 2, psi A R1, psi B R2, plus psi B R1, psi A R2. But you will argue with me that this is a bosonic wave function and it's symmetric under exchange. But it's only symmetric and it appears to be symmetric under exchange, and indeed the spatial part is symmetric under exchange, but it's the entire wave function that has to be anti-symmetric under exchange. So you multiply this or tensor product with the spin wave function that is anti-symmetric under exchange. So, and that is just a singlet state. So you take the direct product of this spatial wave function of this symmetric under exchange, which enables the formation of a bond with the singlet state 1 over under root 2 plus half minus half, where these are the labels for ms, these are the values of ms, the spin quantum numbers. Half minus half minus half. Okay, so this is the spin wave function. Now this is a total wave function that comprises the spatial part and the spin degree of freedom. This total wave function is anti-symmetric under exchange, and this is what is required for two fermions. The total wave function has to be anti-symmetric under exchange. You can't just focus on the spatial part. So if a bond is formed, necessarily the two electrons are in this spin, have this spin wave function. The spins are opposite in other words. But they're not in either this state, plus half minus half, neither in minus half plus half, they're in a superposition. Because this has a definite parity, this has a definite action under spinning, under exchange. So this is the total wave function for two electrons that form a covalent bond between two hydrogen atoms. And it's a total wave function that has to be anti-symmetric under exchange. So one has to take into account the spatial part of the wave function as well as the spin part of the wave function. Now in parahydrogen is the spin part of the nuclei. There is the rotational wave function which has a definite parity. You know that it's minus 1 h bar L. This is the nuclear part. There's a ground state electronic part. There's the rotational motion part. All of these coupled to give you a special kind of wave function for parahydrogen. So this is something that you should explore on your own. Alright, so today inshallah we also post you quiz solutions. Please submit your homework today.